Hello, ladies and gentlemen. We're going to do 2.5 and 2.6 today. So we're going to talk about implicit differentiation and our related rates. So we use our implicit differentiation to find the derivative of a function, and then we're going to review and explore our related rates. So in section 2.5, we want to go back before we actually get started and talk about the explicit form of an equation. So even though we don't talk about it being an explicit form very often, it would look like y is equal to 3x squared minus 5. And what I notice when I look at the explicit form is that y is over here by itself. Everything over here is either an x or a constant. And so if I take the derivative of this side, the derivative of y is dy dx, and then the derivative on this side is 6x. Well, if I needed to find the slope of a tangent line, it's right here. I could substitute in values, and I'd be good to go. But then an implicit form looks like this. So it might be as simple as xy is 1, because it's not in terms of y, so it's implicit. But on this one, I could actually solve for y, and I would get 1 over x, and then I could take the derivative. Right? So if I wanted to, I could take the derivative, and that would be fairly straightforward. But what if my equation looks something like this? X squared minus 2y cubed plus 4y is 2. So if I try to isolate y and solve for y, it's really a little bit difficult. And if you'll remember, when I do implicit differentiation, when I take the derivative of a y term, I get the derivative of y with respect to x, and then when I take the derivative of this with respect to x, this is how I got this expression. So when I take a derivative with respect to x of an x term, I'm a happy camper. But when I take the derivative of a y term, it's not in terms of x, so it's going to generate a dy dx. We're going to solve for the dy dx's, and then we'll be able to find the slope of our tangent line. So let's take the derivative of this guy, just as a reminder, and I would get 2x minus 6y squared. Remember, I'm taking the derivative of a y, so it generates a dy dx, plus 4 dy dx, that's d, and then the derivative of a constant is 0. So the goal is to solve for dy dx because I want to be able to calculate the slope of the tangent line. So I'm going to isolate and factor out my dy dx's. So I'm going to get dy over dx. When I factor, I'm going to get a negative 6y squared plus 4. I'm going to move the 2x to the other side. The goal is still to solve for dy dx, so I solve by dividing, and I'm going to get a negative 2x divided by a negative 6y squared plus 4. So if you'll remember, at this point, I have a generic formula to allow me to solve for the slope of the tangent line. But in this case, I would evaluate it at a point, but to calculate the slope, all I have to do is substitute in x, and then I can get the derivative at that point. But in an implicit differentiation, when I evaluate my generic equation at a point, you'll notice that I have to substitute in both the x and the y values to come up with the slope of the tangent line. Okay? So that's just some little differences between explicit form and our implicit form. All right, let's do an example. Okay. All right, so I want to find dy over dx, and I'm going to be given the equation y cubed plus y squared minus 5y minus x squared is a negative 4. Now, I could, if I wanted, move the x's to the other side in the beginning, and on this one, that's not so difficult. So I might do that to start. So I would have y cubed plus y squared minus 5y is a negative 4 plus x squared. And now if I take the derivative of both sides, I'm going to get 3y squared dy dx plus 2y dy dx minus 5 dy dx. And remember, I'm generating a dy dx because I'm taking the derivative of y with respect to x, but because the variables don't match, then I have to include that notation, and then I'm going to get 2x on this side. Now I'm going to factor out my dy dx's, so dy dx, and I'm going to get 3y squared plus 2y minus 5 is 2x. I'm still trying to solve for dy dx, so now I'm going to have dy dx is equal to 2x divided by 3y squared plus 2y minus 5. And then I could substitute in my point, if that was the purpose of the problem, and find the slope of a tangent line at a given point, x and y. And again, noticing that I have to substitute in both the x's and the y's. Alrighty, so let's do a problem that's a little bit more entertaining, just as a kind of longer example for our implicit differentiation. So we want to find the tangent line to the graph, and we're going to be given x squared times x squared plus y squared equals y squared at the point, and our point's going to be radical 2 over 2 and radical 2 over 2. Now, it might be easier if I unrationalized these and just did it as 1 over radical 2, but I'm not going to do that because if I change things, I always screw it up. So, the way that I'm going to start is I'm going to start by distributing. So I'm going to get x to the fourth plus x squared y squared is equal to y squared. So I was assessing whether or not I wanted to distribute or do the product rule from here, but I think this will be easier. So now if I start taking my derivative, I'm going to get 4x cubed plus, this is the product rule, so it's the first thing times the derivative of the second thing, remember that generates a dy dx, plus the second thing times the derivative of the first equals 2y dy dx. Okay? So now what I need to do is I need to get all of my dy dx's together and everything else can stay on the other side. So I'm going to have 2x squared y minus 2y, and then I'm going to do my dy dx, okay? And then taking these terms to the other side, a negative 4x cubed minus 2xy squared, okay? Now I'm still going to solve for dy dx, so dy dx is going to equal, and I'm going to factor a 2 out over here just to make life a little bit simpler. So I'm going to get a negative 2x cubed minus xy squared, because these guys all have 2's in it. And I'm going to divide by a 2 factored out, x squared y minus y. Alrighty. I could factor out an x on the top and I could factor out a y on the bottom, but I don't know that that's actually going to do me any good. The 2's do cancel, and so now I'm at a point where I can substitute in the point that they gave me, and it's not a very polite point, okay? So if I substitute in that math, I'm going to have a negative 2 times radical 2 over 2 cubed minus a radical 2 over 2 times radical 2 over 2 squared over radical 2 over 2 squared times radical 2 over 2 minus radical 2 over 2. That is a lot of stinking radicals. Alrighty. I'm going to simplify on the top. So I have a negative 2. Radical 2 squared is times 2 radical 2 over 8. And then this is going to be a radical 2 cubed, so it's going to be 2 radical 2. This is 4 times 2 is 8. Well, isn't that polite? Okay. And then on the bottom, I have 2 radical 2. This is squared, so this is an 8 minus radical 2 over 2. And I'm out of room, so I'm going to go to another sheet of paper. I'll rewrite it before I clean it up. So I have a negative 2 radical 2 over 8 minus 2 radical 2 over 8. And then in the bottom, I have 2 radical 2 over 8 minus radical 2 over 2. Okay? So if I clean this up, actually I could, that would be okay. So I'm going to circle my negative so I don't lose it. 2 goes into 8 4 times, and 2 goes into 8 4 times. Yes, I know I have another 2, but I can't put my fractions together if I do that. And then down here, I'm going to multiply by 4 over 4. So on the top, I have a negative. I have a 2 radical 2 minus radical 2 over 4 over 2 radical 2 over 8 minus 4 radical 2 over 8. Clean this up a little bit more. So this is a negative 3 radical 2 over 4. And this is a negative 4 and 2 is a negative 2 radical 2 over 8. These guys are going to cancel. That's polite. So now I have a negative 3/4, and then I have 8 over a negative 2. Okay, so 4 goes into 8 2 times. The 2's cancel. The negatives become positive. Yippee! I got the right slope. Okay, so I know that from all this mess that the slope of the tangent is 3. But we're not done because they asked me to write the equation for the tangent line. I use my point slope formula, m times x minus x1. So, and I'm going to use the only point that we have, which is kind of gross. Y minus radical 2 over 2 is 3 times x minus radical 2 over 2. Clean it up. Y is 3x minus 3 radical 2 over 2 plus radical 2 over 2. My tangent is 3x. A negative 3 plus 1 is minus 2 radical 2 over 2. 2's cancel. So finally getting it all cleaned up, I get 3x minus radical 2. Whew! And you can't see it, but there is the slope of, there is the equation for the tangent line. All right, so that was exciting. Let's go do 2-6 now, and let's talk about related rates. And remember, these can sometimes be pretty challenging just because I have a lot of information to manage. And in my notes, I called this our beloved concept. You know, it's enduring, right? So just to review some terminology, if I have dy dx, that means the derivative, sometimes I have a hard time spelling that word, of y with respect to x. And then if I have a dv over dt, this is the derivative of the volume with respect to time. Okay? And you get the general idea. So remember, when I do a related rate problem, I often end up with a lot of different notations within the same problem. So let's go back and talk about some of our helpful hints. The first one that I would advise you to do is to write everything down that you know. So write down everything. And when you write down everything, you need to make sure that you're labeling it with the appropriate notation so that you know that you've been given a rate. You need to label it as such. And then if you need to, you can draw a picture, because oftentimes on these we need pictures to help us remember specific pieces about the math that we're going to do. Then I want to write an equation whose variables and rates of change are given. And sometimes I need to write an equation of what I am looking for. Okay, so I can often have at least a couple of different equations going around. The next thing that I'm going to do is I'm going to find my derivatives of the equations that I've written, and I have to be careful with my implicit differentiation, meaning that you could potentially have lots of different variables floating around in your equation. And since I have many variables floating around, I need to make sure that I include my specific derivative notation because then I can use that to solve. The next thing that we're going to do is we are going to substitute in our known values, and then I'm going to solve. The one piece about related rate problems that gets to be fairly difficult is sometimes once I write an equation, I have too many variables and I don't have enough input, so then I often have to write an equation that will help me to eliminate the extra variable. All right, so let's do an example to start. It's a very traditional problem when we start doing our related rates. This one says air is being pumped into a spherical balloon. And I bet you could guess what I was going to write. Oops, except I spelled it wrong before I even got there. At a rate of 4.5 cubic feet per minute. And in the problem, I just wrote those words out, but in the essence of time, I just abbreviated it, which is nice because that tells you what your rate is. Find the rate of change of the radius when the radius is 2 feet. All right, so if I practice what I preach, the first thing I'm going to do is write down everything that I know. First, it tells me that air is being pumped into a spherical balloon, and they give me a rate. Well, the rate that they give me talks about how the volume of the balloon is changing, so I know that I have a dV dt is going to be the 4.5, and always write your units down because it will help you later. Well, if the volume is changing, then I write down an equation for the volume of a sphere is 4/3 pi r cubed, because volume is always a cubic thing. And then I want to find the rate of change of the radius. I'm looking for dr dt. And if you look at the information that you've been given, I can take the derivative of the volume, I know that number, and I know a specific radius, and I'm going to get a dr dt, so this one's actually fairly straightforward. So the first thing that we're going to do is we're going to take the derivative of the volume formula. So when I get dV over dt, it's going to equal 4 pi over 3 times 3r squared. Don't forget your implicit differentiation, dr dt. This little guy is who we're solving for. So if I substitute in, and I'm actually going to clean it up a little bit, so I'm going to get and rearrange dr over dt is going to equal dv dt divided by 4 pi r squared. And remember they said find the rate of change when the radius is 2, so I'm going to evaluate this when the radius is 2. I know dV dt, so I know everything. So dr over dt is going to equal my dV dt, 4.5, divided by 4 pi. My radius is 4, because 2 squared is 4. And then if I clean that up just a little bit, I get 4.5 over 16 pi. And then when I do that math, I get 0.09. Our units are feet per minute, right? And I know that it's linear because a radius is linear. So dr dt, you always want to be really careful with your units, except you can't see what I'm writing, feet per minute, all right? So one of the things that this problem says, if you think about the results that you got, the volume is increasing at a constant rate, And they gave us that rate, so the volume is increasing at 4.5 cubic feet per minute. The radius is changing. Oh, I'm sorry. I did get it in there. Is changing at a variable rate. And what that means is as the balloon gets bigger, the radius is changing. So it's not a consistent radius change. The volume is changing constantly, but the radius is changing at a variable rate. So then another conclusion that we could make about that, it says the change in the radius is slowing down. And I know that because this is a percentage and so it's decreasing. If it had been a 1 point something, then it would have been increasing. But because it's just a decimal, that means that it's actually decreasing. All right, I have one more example just because I feel like we need more examples of related rates. So this is our last example. This one says the altitude of a triangle is increasing at a rate of 1 centimeter per minute. Oops, I need to put minute there. While the area of the triangle is increasing at a rate where am I? Is increasing at a rate of 2 square centimeters per minute, because we're talking about area. And then the question is, at what rate is the base of the triangle changing? Because teachers have to come in and interrupt me to get coffee, which is entertaining. When the altitude is 10 centimeters, ooh, that's a lot of writing, and the area of the triangle is 100, that's 100 centimeters squared. All right, that's a lot of words. So the altitude of a triangle is increasing. So I'm going to draw me a cute little triangle. There he is. And I'm not going to call my altitude A because I have an area, so I'm going to call him H. This is obviously going to be my base. It says the altitude is changing, so dH over dt is changing at a rate of 1 centimeter per minute. And remember, we're talking about distances, so this is all the units for our measure because this is linear. And then it says that the area, so dA dt, is changing at a rate of 2 square centimeters per minute. At what rate is the base of the triangle changing? So I'm looking for dB dt, and then I'm going to be given when h is 10 and area is 100. So the first thing that I'm going to do, I drew my diagram. I'm going to write the formula for the area of a triangle, and I know that area is equal to 1/2 base times height. Well, I don't have a number for the base, so I'm going to use these two values to solve for the base. So the base is going to be 2 times the area divided by the height, which is going to be, do I want to do that? I did something wrong. Let me look at what I have, 1/2 base times height. 1/2, 10, that's 5. I think I'm good. Yeah, sorry, brain fart. So I'm going to have 2 times my area, which is 100. I did it a different way, and then my brain had a brain fart. So a 0 cancels, so I end up with a base of 20 centimeters. Whew, that was rough. All right, so now I'm going to use my handy-dandy little formula, and I'm going to start taking the derivatives of everything. So I get that dA dt, because the area is changing with respect to time. The half is going to stay out here. And then b times h is the product rule, so it's the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. All right? And if you'll remember from the information that we wrote down, this is what we're actually trying to solve for. So I know that my dA dt is 2, so I'm going to write 2, and I'm going to multiply that 2 by this 2, so 2 times 2, all right? And then over here, the base is 20, and then my dH dt is times 1, and then plus my height is 10, and then I'm trying to solve for dB dt. So then I'm going to get 4 minus 20. Let me scoot it up a little bit, sorry. So 4 minus 20 is going to equal 10 dB dt. So then my dB dt is going to be a negative 16 divided by 10, which is a negative 1.6. Remember, my base is a linear unit of measure. The measure that I have is centimeters per minute. And then I just write my final answer so it's nice and pretty. So dB dt is a negative 1.6 centimeters per minute. So that was it. That wasn't a horrible example. You know, they get a little bit more entertaining as we go. But I hope that was a good review. I'm going to wait